What is going on, everybody? Today we're going to be doing some proofs. One proof in two separate ways, actually. We're going to be trying to prove this little guy right here, the derivative of ln of x, which, as we know, is equal to 1 over x. But why? That's really the question we want to know. So we're going to be proving it once implicitly. And another way we're going to be solving it is by finding the limit of the difference quotient down here in the bottom, which I put there just for reference in case you've forgotten it. And that'll utilize some of the things from your Calculus 1 class. And also want to keep in mind the definition of E. This is not the only definition, but it's a definition that we will use. So it's important to remember that as well. So let's go ahead and jump into doing the very first proof, and this one is just implicit differentiation. So remember, we're trying to prove that derivative of ln of x is equal to 1 over x. So first, let's just start and let's just say let y equal ln x, okay? And this is kind of a similar method that we did in my last video where we proved the derivative of log a of x is 1 over x ln b, or 1 over a ln x, whatever it is. Anyways, for this one, it's a similar method where we're going to get to utilize e. And in doing so, if we raise e to both sides, we get e to the y equals e to the ln x. And as we know, whenever we have an e to the ln x, that just drops. So that becomes e to the y equals x. Using this knowledge, we can go ahead and implicitly differentiate e to the y equals x. So if we take the derivative of the left side, we're going to have e to the y times dy dx, because remember, whenever we're doing this with respect to x, so whenever we try to differentiate y, it has to be done implicitly. And then the right side, the derivative of x, that's just going to be 1. So what we do here is we go ahead and divide by e to the y, and we have dy dx equals 1 over e to the y. And as we remember from up here, e to the y is equal to x. So therefore, when we go back, we can just rewrite this entire equation as dy dx equals 1 over x. And that is how we prove for implicitly that the derivative of ln of x is 1 over x. So now let's go into the more fun one. This is the one where we get to do some implicit differentiation, the limit of the difference quotient. That's the more fun one. And we really get to get into a lot of interesting techniques in this one. We really combine a lot of concepts from a lot of math classes in one. So as you remember, we have the limit of the difference quotient. This is basically the fundamental way of finding a derivative. So let's just go ahead and write out our definition right here. So if we were going to be finding the derivative of ln x, our difference quotient would look like this. The limit as h approaches 0 of ln of x plus h minus ln of x all over, I'm actually going to bring that up a bit. It's a bit low. All over h. So it's important here to remember some of our laws of logarithms. And we can remember that whenever you're subtracting two logarithms, that's really the same as if you were just adding them. So we can go down to this next step. We can just say the limit as h approaches 0 of ln of x plus h over x all over h. So now you might be thinking, what should we do here? So let's combine two steps actually in this one. What I'm going to do is I'm actually going to pull out this 1 over h to the front, and I'm going to go ahead and simplify some fractions in here to make it a bit simpler. So we have the limit as h approaches 0 of 1 over h ln of 1 plus h over x. Okay? So we've simplified that, and just to make sure you follow what we're doing here, we pulled out this inferred 1 over h to the front. And then we just made x over x1 plus h over x. You can split it whenever there's more terms in the numerator than there is in the denominator. So let's go ahead and now we get to use one more rule of logarithms. And that is that whenever you have anything in front of an ln, you put that to the power. Basically, this 1 over h right here can be moved right here, and vice versa. If there was an ln to a power, it could be brought to the front. So, in doing so, we can rewrite this as the limit as h approaches 0 of ln, I'm going to put some brackets here actually, of 1 plus h over x to the 1 over h. And that is an h, not an n. So now we're here, and we really have to think of what the next step might be. And I'll go ahead and tell you, because these proofs do get tricky, and it's hard to follow the intuition unless you really know sort of a special way to do it. But I'm going to go ahead and knock some of this out for you. So we have that. That's where we are currently. Let me go ahead and get this out of the way. So now let's go back up here and let's begin. So let's start thinking maybe we want to do a u sub here. So we could say let u equal h over x. Okay, so if we let u equal h over x, we have that. We would have 1 plus u, right? And then what we also may want to do, just as a future reference, is say ux equals h. And I'm sure you all see how that is. And that is just so that we can replace this h right here with u to make sure that we change, because whenever you're doing a u sub with a limit, this has to change, this has to change, and this h has to change. We have to be taking the limit as u approaches 0, which is a completely different thing than h. Totally, we're in u world now. So let's switch back and let's rewrite this at the top. We now have the limit as u approaches 0 of ln of 1 plus u to the 1 over ux. So everything has its proper respects now. So now what I'm going to do, and like I said, this requires a little bit of intuition because we don't quite, but you kind of can start to see if you look over here, you can kind of start to see a correlation between this and e. We're starting to see a bit of where it looks almost to be exactly the same. So this is what we can do. We can actually, well, we'll find e in a second. Let's go ahead and simplify this one more step, and let's try to get it to where it's about ready for us to finish out and put everything back in the original variable. So let's split this up, and we can actually, what we can do as well, this is actually a rule of limits. Whenever you're taking the limit of something and you know it's going to be the ln, this is the same as if we just pulled the ln out to the front and we said ln of the limit. So that would look something like this. It would be ln of the limit, and I'm not a big fan of the bracket notation with the ln. I really like that. So we have the limit as u approaches 0. Now I'll use the brackets of 1 plus u. Let's go ahead and do like this, to the 1 over u. And all that's going to be to the 1 over x. And we can go ahead and close that last bracket off. So now you can start to see we're really getting close to where we could define this, to where we could define e as this. So now what we're going to need to do is let's make some space for ourselves at the bottom here. And let's try to do some u subs with e to make it look just a little bit like what we have here. So remember, we have e up top. I'm not going to rewrite it, but what we're going to want to do is we're going to want to make a u sub. So, excuse me. we're going to want to set u equal to 1 over n. So what we can do is, like I said, have u equal to 1 over n. And then in doing so, when we actually say when n is approaching infinity right here in E, sorry if that's hard to read, I'm referring to the top left when n approaches infinity. Well, when u approaches infinity, 1 over n approaches 0. So we can actually rewrite the definition of E as E equals the limit as u approaches 0 of 1 plus u. And now what do we want to do? We have a 1 over n, and we really want to get that n to the top there. So if we take this, we can actually get that n to equal 1 over u just by doing some simple, that is a really bad n. We have n equal to 1 over u. So whenever we have that n equal to 1 over u, that's exactly what we have here actually. So if this was to the n, then we could say this is to the 1 over u. So now we have effectively created the exact same definition here. So if you can note, this definition is the exact same as what we have made here, right? And there's some real intuition to that, that we're dealing with an ln. And you may see, some of you may see where we're going with this, but let me clear out some space on the side here and let's finish this problem up. So if that is the case, then what we can do is actually, get back here, we can finish out this problem by saying we have ln, and remember the inside is the same as e, ln of e to the 1 over x. And if you remember, ln and e are inverses of each other. So these two are going to cancel out, leaving us with just 1 over x. And that is the proof of how we could find that with the difference quotient. The limit of the difference quotient, excuse me. There's a lot of fundamentally different ways to find this proof, but I find this is an extremely elegant and kind of a fun way to go about doing this, because you go and you find E and you U sub and you do U subs with ln, and you really get to go through a lot of different steps. So I really hope you guys enjoyed this video, and I'll be definitely bringing out some more proofs soon. Peace.